In lesson 5.5, we will discuss complex numbers. We'll jump right into the definition. A complex number z, so we're going to use z to represent our complex number, is a number that can be expressed in the standard form a plus bi, where a and b are both real numbers and I is the square root of -1. We're going to have different types of complex numbers, and we'll talk about those. So an imaginary number is a number in the form a plus bi where b does not equal 0. So as long as it has an I in there, it's an imaginary number. So we might have 3 plus 2i. Again, a and b have to be just real numbers. So it could be square root of 7 minus square root of 2i. It just says b can't equal 0, so a could equal 0, so we could just have something in the form -5i. So all these are just examples of imaginary numbers. Next, pure imaginary numbers is an imaginary number, so it has to be like this, where a equals 0. So our a term is equal to 0. So this would fit that form. So we have -5i, which just mentioned from above, I, -3i. We could have roots in here. We could have like the square root of 41i, which is a lot of times written as I times the square root of 41. Oops, it's supposed to be a 4. So those are pure imaginary numbers. They only have the imaginary part. And then real numbers is a complex number where b equals 0. So that just gets the real part. So 7 or 2/3 or square root of 5. We've already talked about real numbers. They don't have this imaginary part, but what this is saying is that a real number is a type of complex number. So here we see that the set of complex numbers is the union of imaginary numbers, so the imaginary numbers and the real numbers, and that's all the complex numbers. We can graph complex numbers similar to an x-axis and y-axis to the Cartesian plane. But instead, we're going to have a real axis and then an imaginary axis. And we see here, we want to graph 3 minus 4i. Well, that just means 3 is our real part, so we get a 3 on the real axis and -4i on the imaginary axis. And there is the point, 3 minus 4i. We have -3i. Well, there's not a real part there, so we're just at 0 on the real axis, and then we want to go to -3i, which is there. -2 plus I, we're at -2 on the real axis and I on the imaginary axis, and then 5, just 5, so that's a real number, so we're on the real axis, 5. So there's those 4 points. Very simple to graph. This next part, we're going to talk about absolute value of complex numbers, and we can still think of our definition as a number's distance from 0. And we still use these symbols for absolute value, so we might see absolute value of z, because a lot of times that represents an imaginary number, or you can have absolute value around the number, and it is always going to equal the square root of a squared plus b squared. So the square root of the real part squared plus the imaginary part squared. To find the absolute value of these, we can use this formula right here. In a minute or so, I'll show you why this works, but let's just use the formula. So the absolute value of 3 minus 4i. By this up here, we can just do the square root of 3 squared plus -4 squared. Notice I don't put the I in there because b is not, I is not part of the imaginary part there. So we have 3 squared plus -4 squared. Well, this is 9 plus 16. 9 plus 16 is 25, so we have the square root of 25, which we know is 5. So the absolute value of 3 minus 4i is 5. Let's move on to this next one here. The absolute value of 3i, -3i. Well, there's not a real part. There's not an a because it's not a real part, so we just want to do the square root. Well, we can put 0 in there. 0 squared plus the imaginary part squared, so negative 3 squared. And that's going to equal 0 squared is 0. Negative 3 squared is 9. The square root of 9 is 3. So the absolute value of negative 3i is 3. The next one we see here, we want to find the absolute value of negative 2 plus I, which is going to equal, once again, the square root of a squared, so negative 2 squared, plus, and what's our b here? Well, that's a 1. The coefficient's 1, so plus 1 squared. And that will equal 4 plus 1. So that's the square root of 5. So the absolute value of this is square root of 5. And then the last one, well, this is the absolute value of 5. Well, we already know what that is. It's a real number, so we don't even have to use our formula up here. We can look at it just to show that it does work. Our real part squared, well, that's 5 squared. Plus the imaginary part squared, well, there is no imaginary part, so that's 0. And so we have the square root of 25 plus 0, which is 5, which we already knew the absolute value of 5 was 5. Let's take a look back at the graphs of these. Now remember, it's the numbers distance from 0, and so 0 here on the complex plane is just the origin right here. So this is 0, because it's 0 plus 0i. And so if we want to think of this distance here, these are the same numbers. So negative 3, or 3 minus 4i, that was down here. If we wanted to find this distance, we could use Pythagorean Theorem. And what's this length? Well, that's our real length. That was 3. And this was negative 4. So we went down 4. So the distance is still 4. And how do we find the hypotenuse of a right triangle? Well, we do Pythagorean Theorem. So we have 3 squared plus 4 squared equals that distance from 0 squared. And just to show the formula, they're just taking the square root of both sides here. And we see we have the real part squared plus the imaginary part squared, which we could have put as negative 4 here. And we square that. So it comes from the Pythagorean Theorem. These two here, these two circled ones, are really easy because, again, we're looking for the numbers distance from 0. Well, this is 5 units from 0, so the absolute value of 5 is 5. And if we have a pure imaginary number, all we have to do is look at this part. The absolute value of that is just 3. So it's 3 units from 0. So pretty easy to do absolute value. We can use this equation here, or we could graph it and find the distance using Pythagorean Theorem. We have operations we can do with complex numbers. Adding or subtracting. You add or subtract the real parts and add or subtract the imaginary parts. It's kind of like adding like terms. Multiplying, you just distribute. Remember, we mentioned before I squared equals negative 1. We'll actually carry this out a little further later. But if you ever come across an I squared, you want to change that to a negative 1. So looking at these very quickly, these are just adding two complex numbers. We can add the real parts. So 5 plus 6 is 11. And then 2i plus negative 3i is negative 1i, or just negative I. Next one is subtraction. Since we have a minus here, we can go ahead and distribute that. You can go ahead and just do that in your head also and do the subtraction, but here we have it written out. So negative 2 and negative 4 is negative 6, and negative I plus 7i is 8i. Here we just have 3 complex numbers added together. Adding's okay. Here's subtracting, so I'm going to go ahead and change this again. So we have 3i plus negative 2 plus 5i. This negative is distributed, so we have plus 2 minus I. And now we can look at like terms. 3i plus 5i is 8i, minus I is 7i. And then negative 2 and positive 2 is 0. So our answer is 7i. Now we're going to go ahead and look at multiplying. So this is just a 4i multiplied by 2 minus 3i. We distribute. So we have 8i. 4i times 2 is 8i minus 12i squared. Now remember, I squared is equal to -1. So we have -12 times -1, which gives us 12. And we actually like to put the real part first. So we have minus -12, which is positive 12. So we have 12 plus 8i. We want to put it in that a plus bi form. Here we distribute again. So 6 times 2 is 12. 6 times 4i is positive 24i. Now we have -i times 2, which is -2i, and -i times 4i, which is minus 4i squared. We have a couple like terms here, so we can add those. So we have 12, we have 22i, and remember this is equal to -1. So if we have -4 times -1, that's plus 4. And now we see we can add these 16 plus 22i. And the last one here, this is actually an important concept that we'll discuss a little bit later also, but we can see what happens here. We should recognize this form. This is 2 plus 7i, then 2 minus 7i. So we'll multiply it out, but as we see these, there's a quick pattern we can do. So we have 2 times 2 is 4. 2 times -7i is -14i. So we just multiplied that. 7i times 2 is plus 14i. And then minus 49i squared. These are opposites, so they become 0. And we have 4. Remember, I squared is -1. So we have -49 times -1, so that's plus 49. So we actually get 53. Real quickly here, we should recognize this as it's going to be a difference of squares. So it's going to be the first thing squared minus the second thing squared, so 7i squared, which is 4 minus 49i squared. Sorry, that's supposed to be a 4, 49i squared. And I squared is -1, so it's 4 plus 49, which again is 53. The last thing we're going to do here is look at powers of I. So we know the square root of -1 is I. And so we use I. And we've already talked about that I squared is equal to -1. If you want to know why that is, you have -1 squared, and the squared cancels with the square root, and you get -1. Well, that means I cubed we could write as I squared times I by rules of exponents. Well, we know I squared is -1, so this is actually just equal to -1 times I, which is -I. And then I to the fourth equals, well, we know rules of exponent, that's I squared times I squared, which I squared was -1, so that's -1 times -1, which is 1. And then we actually end up with a pattern here. If we kept going I to the fifth, well, we can just think of that as I to the fourth times I, which I to the fourth is just 1. So that's I. And this can continue, I to the sixth. We can think of as I to the fourth times I squared. So this is just going to be equal to I squared. And we have this nice pattern. So I is obviously equal to I. That's as simple as it goes. But then we have these other things. I squared equals -1. I cubed equals -I. And then I to the fourth equals 1. And then this pattern keeps continuing, keeps going and going. And so what we can see here is if there is, if your exponent is a power of 4, sorry, is a factor of 4, it's just going to equal 1. And those are important. So what we're going to do is we can divide our exponent by 4, and whatever the remainder is, if we look at our exponents, whatever the remainder is will be what it corresponds to. So if we have a remainder 1, that full thing will equal I. If we have a divide by 4 and have a remainder of 2, it will equal -1. Remainder of 3, it will equal -I. So let's take a look at this. I'll talk through the first few here. So if we have I to the 11th, what we're going to do is we're going to take 11, divide it by 4. That goes 2 times with a remainder of 3. Well, what I'm saying here is if we have a remainder of 3, that corresponds to I cubed. So I to the 11th, I to the 11th is really equal to I cubed, which is equal to -I. This one we can take 28. 28 divided by 4 goes in 7 times with no remainder. So no remainder corresponds with just this one, because it's a multiple of 4. So if it's a multiple of 4, which 28 is a multiple of 4, it's just going to be equal to 1. So I to the 28th is equal to 1, because the remainder was 0. Divide 97 by 4. Now, there are some things we can think through and do some of these things, but let's just do this. This is going to go in twice. We have 8. Subtract, we get 1, bring down the 7. That goes in 4 times. 16, subtract, and we get a remainder of 1. So this 24 really doesn't matter to us. The remainder 1 is what we're concerned about. So if we have a remainder 1, we look here, this will just be equal to I. So I to the 97th will be equal to I, because that's what I to the first was, that remainder 1. 12,143. So we want to take that. We're going to divide it by 4. That goes in there 3 times. Again, this number that we divide here doesn't really matter. We'll bring down the 1. 4 goes into 1 0 times. Bring down the 4. 4 goes into 14 3 times. 3 times 4 is 12. 2, bring down the 3. 423 is 5 times. And we get a remainder of 3. This doesn't matter. It's the remainder of 3 that matters. So we look up here. Here's the 3. And so I to the 12,143 is simply equal to I cubed, because our remainder was 3, so this equals -1. And so there's how we can simplify powers of I.